Hey everybody, Mr. Bell's here again. This is a video lesson coming to you in geometry for section 4-5. And this one is going to be our last series in the transformation sections. Again, so far we've done translations, right? Reflections, rotations. And then we did a whole section of compositions of transformations, which could be combinations of them, like glide reflection, like that has a reflection and a translation in it. So the last one we're going to do is one that all of a sudden doesn't keep rigid motion anymore, and that's called a dilation. So a dilation is going to take something that's small and make it bigger, or something that's big and make it smaller. We're going to do those coordinations. You're going to find out that even though the shapes aren't congruent anymore, if the scale factor is the same on both of the dimensions, the length and the width, then it's going to be something that's called similar, which means the sides aren't going to be the same, but the ratios between the sides will be the same. So here we go. This is tighten this camera up so you can see it here. And I'm going to do a quick little talk about it just on some regular paper right now. Again, we will use our student journal because I think that's easier for you guys to be able to see some of this stuff. So what is a dilation? So this would be an example of a dilation, and what would kind of happen is this. If this was to grow to be this big and it was a scale factor, maybe this original thing was 3 inches long, then this one would be, let's say 6 inches long. And if this top part right here was 1.5 inches, then this top part right here would be 3 inches, and you would see that the scale factor is 2. Okay, it's going to grow by 2. So if I was to coordinatize this, that any xy that I had right here would become new points of 2x, 2y. That we simply multiply each xy coordinate by whatever the scale factor is. Now, typically, what they'll have is a center for that dilation, and if this was perfect, and again, I just sketched this off. If this was perfect, I would be able to connect from one point through its corresponding point. So if this was A and this was A prime, and from B, and this was B prime, that if I connected these points through here, that the point where those lines intersected between those things would be the center of dilation. And most of the ones that we're going to talk about in this class is ones that will go from the origin. Okay, so center of dilation. Now, if this was perfect, if this was perfect, then you would see that I would be able to also draw from this point right here to this point right here, and that would also go through the center of dilation. And from this point right here to this point right here, that would also go through the center of dilation. And those would be kind of just like a whoosh, and you can kind of see that three-dimensional blow up now between those, or two-dimensional blow up between those. Okay, so that's what a dilation is. And again, if it grows, the textbook calls it an enlargement. And if it shrinks, the textbook will call it a reduction. Okay, so those are our two kind of things, and how do I find this thing? If I was to take the distance from, let's call this point F. If I was to take the distance from F to A prime, and divide it by the distance from F to A, whatever that is would be my scale factor. Okay, So again, if you look at this big picture, F to A prime, that's the long distance, right? And F to A, that's the short distance. That if these things were doubling, like I said, 3 to 6 and 1.5 to 3 inches, then this distance would be twice as much as this distance right here. Okay, scale factor. Okay, so now let's look in your student journal at a couple of these different things. You can see right here some extra practice problems. This is page 115, page 115 in your student journal. You can see that this shape right here says find the scale factor of the dilation, then tell whether the dilation is a reduction or an enlargement. So this was your original one, right? And this is your new one. Okay, so we can see that it's a reduction. I'm hoping we can see that it's a reduction because it went from big to small. So this one, reduction, reduction. And we have to go the distance from here, the pre-image, or the image to C, over the original one. So that would be a 2 over a 4. So the scale factor is 1/2. Okay. This one right here, you can see this is your original triangle. CP, let's call this D. We can make this D prime too. So CPD becomes CD prime P prime. So it got bigger, so it's an enlargement. Enlargement. Good deal. And again, we're going to take the image distance, right? The image distance over the pre-image, or the original. So this would be a 25 over a 20, or a 1.25 enlargement, or if we want to reduce, we can call it a 5/4 if we want to just reduce that fraction. Okay, this one right here, again, this was your P prime, this was your original, so the original got much bigger, so this is an enlargement, and it would be 27 over 9, or 3-to-1 ratio, or 3 times as big for the sides. But I want to point something out right here before we move on to the next thing. Good deal. If this right here, I don't have the numbers, but let's call it 12. Then this one outside here would be 36, right? And if this right here was 10, then this outside here would be 30. So even though the scale factor is 3, if I look at the original shape, its area is 120, but the area of the prime shape is 30 by 36, and we'll pull out our handy dandy little calculators right now here. 30 by 36, enter, 1080. I want to take a look at how much bigger this is, so I'm going to go 1080. I think you can see that. Let me lighten this up for you a little bit. There we go, 1080 divided by 120. And you can see that it gets actually 9 times bigger. The area 1080 divided by 120 equals 9 times as big. Okay? So if we have a scale factor of 3, I guess the big aspect of it is if this is x, then this is 3x, right? And if this is y, then this is 3y. So the area of the original shape is xy, right? But the area of the new shape is 3x times 3y, or 9xy, 9 times bigger. Okay? And it really is 3 and 3. So likewise, hopefully this makes sense. If I had a shape whose scale factor was 5, and I wanted to know about its area, since the 5 would affect the length and the 5 would affect the width, then its area actually would become 25 times greater. So it's whatever the scale is times itself, because that 5 affects both the length and the width when we're talking about these ones. Okay? Let's bring this back up here again. And you can see some of the stuff. You can even try some of the ones on the thing right here. Here we go. I'm going to go ahead and do this one with you, and I'm going to call that good, because I think this stuff makes a lot of sense. So negative 10, 0. So negative 10, 0. There's our P, and then negative 5, 0. Negative 5, 0. That's our Q. And R, 0, 5. 0, 5, that's R. And S, negative 5, 5. Negative 5, 5. Right there. Oops. 0, 5. Sorry about that, R. Didn't count for either one of those boxes very good. So I got this thing right here. Awesome. And now I want to do it on a scale factor of 1/5. So P prime would be 1/5 of that. So P prime would equal negative 2 comma 0. Q prime, which is 1/5 of that, would equal negative 1 comma 0. R prime would equal 0 comma 1. And S prime would equal negative 1 comma 1. Because again, we're just taking all of them and multiplying it by 1/5 or dividing by 5, whichever way you mentally want to think about that. So now P prime becomes negative 2, 0. Oops, let me do it in red, since this is my new one. Negative 1, 0, 0, 1, and negative 1, 1. And it's obvious that you can see that this one has been shrunk down, and it is 1/5 there. But again, its area is 1/25 of the green one, which means we could take 25 of these little red things right here and put it in here over and over and over again, 25 times, to fill up the entire big space of that parallelogram. Okay? To do a quick little formula for you, area formula for a parallelogram is base times height. So base on this first one, 1, 2, 3, 4, 5, and its height is that distance right there, 1, 2, 3, 4, 5. So area of the big one is 5 times 5, or 25 units squared, 25 square units, basically 25 of these boxes would fit inside there. Good deal. Now the area of the red one, its base is 1, its height is 1, which is 1 times 1, which equals 1, and you can see, look, the area is that. And if I do this carefully in green, you can see there is half of a triangle, and this dotted one right here is the other half of a triangle, and that will equal 1 square box. Okay, so hopefully with what we talked about right now, you understand dilations. Please practice these ones in your notes. Try the stuff in the online textbook. Get the homework done. And this is it for transformations. We're all done with that. We'll talk to you later. Thanks.